Example 8, calculator permitted. Given y equals e to the x plus 1 and y equals 2 minus x squared, part A, sketch the graphs of the two functions and identify the region bounded by them. Again, it's a calculator question. You don't want to reflexively grab for it. Look at your functions. They're both easy transformations of parent functions. You can sketch the graph without the calculator's help. Now, I'm not going to be there to stop you from going right to the calculator, but whatever. E to the x plus 1. What does the plus 1 do? Shifts it up 1. So there's the horizontal asymptote at y equals 1, and it's still monotonic increasing looking like that. Passes through the point 0, 2. Ooh, 0, 2, right? That's what I said. That's the next function. It's 2 minus x squared. That's a parabola that has a vertex at 2, and it opens down. Now, when I go out to the right, it looks like that. What's going to happen as I go out to the left? Is it going to be above the curve immediately to the left? Looks something like that, right? Do y'all see the region? If it didn't go above, if you just drew it coming down underneath, then there would be no region bounded by them. It would be infinite on all quadrants. So it looks like it's going to be this tiny little sliver, huh? Now maybe I'd go to the calculator and verify, because I've already thought about the problem. I've looked in the pool. I know there's water in there, so I know if I need to jump in there, I can jump in there. You might also want to check the depth, right? Yeah. Okay, so here we go. E to the x, that's second ln, that's e caret open to the x minus 2. And for some reason, plus 1, I'm putting it in y sub 2. Okay? Now, you know what? I don't know why I put it in y sub 2, but it's already there. I'm not going to waste time typing it into y1. Now, notice up here they have different names, don't they? So here's what I would do. Instead of calling them f and g, because I put the first one in y2 like an imbecile, I'm going to call it y sub 2 on my iPad/paper. And now in y sub 1, I'm going to put the other one, 2 minus x squared. Bless you. Now, I wouldn't normally do that, but it happened that way, and I'm just going to own it. All right, so then there's y sub 1. Now they have distinctive names. Zoom 6. Bless you. Here comes the parabola first, and then e to the x. Oh, yeah. Okay, now, here's what we can do on the calculator. It looks like it's going to be right in there again, and I've already anticipated looking at that. You can go zoom 2, which is zoom in, and that zooms in on a nice symmetric window on each of the x and y axis. Or you could do zoom box, where you define a corner, 2 corners. I like that. I'm just going to kind of hover over there somewhere in the region, hit enter again, and you go in for a closer look. Oh, tiny little smidgen. Y'all want to go one more time? I will. I'm just going to kind of recenter it so it becomes the center of my screen. Hit enter one more time. Remember, the clock's ticking the whole time, so maybe this last one is not necessarily required, but sure is fun. Okay, got it. Now I go to part B. Part B says to find the coordinates of each point of intersection. Show the work that leads to your answer. Okay, first of all, I'm noticing that they're requiring me to get both the x and the y value. So POI, I'm going to set them equal to each other. I'm going to get e to the x plus 1 equaling 2 minus x squared. That's really all you have to do. That's the work that leads to your answer. That's the equation that you're solving to get your answers. Now, I know one of the points, right, should be the y-intercept, 0, 2. I don't want to put x equals maybe. I'll just say the points are 0, 2. And the other one, second trace number 5, enter, enter. If you want to verify that one is 0, 2, you might be doing that, right, because it doesn't take too long. Now, your calculator says it's 3 times 10 to the negative 14th, 2, which to 3 decimals would be 0.000. That's your calculator's way of saying 0. Let's see what the other one is. Second trace number 5, enter, enter, scroll. You can also manually type in an x value if you don't want to scroll. That one there, I'm writing it down to 3 decimals, negative 0.714, comma, 1.489. But what am I going to do with those? I'm going to store them. Now, there's probably a reason they're asking you to find both the x and the y coordinate. So I'm going to store both of them, and here's how I can do that quickly on my paper. I'm going to say that that ordered pair equals A, comma, B. And that defines both A and B. Now, I just got to store them. X stow alpha A, and then Y is alpha 1. So that's pretty easy to remember or get to. Store that as alpha B. And then it'll show up there so you can verify it's the right number. This is anticipating having to use them. That way we don't have to go back and find them. Okay, so I listed the ordered pairs. One was a nice one. One I stored with decimals. Part C, using vertical slices, set up and evaluate the integral that gives the area of the region. All right, so if we come up here, vertical slices, there's my representative rectangle. I'm going to be slicing from left to right. Top curve is which one? The parabola, right? So that's the one that I'm calling now on my paper, stupid me, y sub 1. You may have called it the other way around. But here's what I would do on my paper. The area is going to be the sum of the infinite slices of the top curve, which is y sub 1, minus the bottom curve, which is y sub 2, which is, y'all's maybe is y sub 2 minus y sub 1, dx. And I'm going to integrate from where to where? From who to who? 0 to, from x equals 0 to x equals a, right? From x equals 0 to x equals negative 0.74? Or from a to 0? No, I got it backwards. Yeah, sorry. Yeah. No, I got it backwards. I listed the other point first. If I got it backwards, I guess I could do y sub 2 minus 1, minus y sub 1. I don't want to do that. Okay, from left to right, a to 0, y sub 1 minus y sub 2. Now, if this were truly a calculator test, that right there would get full credit for the setup. You would get like 2 checks for that. And now you go to your calculator, math number 9, and I'm going from alpha A to 0. And for me, it's y sub 1 minus y sub 2, which is alpha trace, enter, minus alpha trace 2. Now, if I had gone from 0 to A on my own, because I'm working independently, the only difference between the right answer and the answer I would have gotten would have been what? I would have gotten a negative. And if I know that I'm finding area, I would, recognize that that's not right, and then I would go back and fix it and be like, something's wrong. One of two things is going to happen. You either have a reversal on your top minus bottom, or you have a reversal on your interval of integration. It's one of the two. Okay, so check those. That would fix it in the beginning, but I would say it's best to just set it up as the integral from left to right of top minus bottom, because that is communicating knowledge of what you're doing. So yeah, it would be okay. What you don't want to do is just erase the negative at the end. You want to go back and fix it. But if you just put a negative in front of the integral, technically that is right. But again, you're not necessarily communicating top minus bottom. So I would say in this case, go back and fix it. Okay, left to right, top minus bottom. All right, so make sure you write it down to 3 decimals, 0.082. Pretty easy little problem when you do it that way. All right, part B, using horizontal slices, find the area of the region. Same thing. Now, for the region, let me redraw it right here. This is my y sub 2. This is my y sub 1. If I'm going to slice it horizontally, I got to change some things. Let me redo this so it looks more like, there we go, it's at the top. Slicing it horizontally is going to be like that. It's a dy. Now, as I slice from low to high, the curve on the right is going to be the e to the x plus 1. Can I solve that for x? I think so. y minus 1 equals e to the x. If I take the natural log of both sides, I get x equals the natural log of y minus 1. That should work. That's the curve on the right. And the curve on the left is 2 minus x squared equals y. If I solve that for x, I get x squared equals 2 minus y. When I take the square root, do I take plus or minus? This is where you got to be careful. Where am I in relation to the coordinate plane? Where's my x values? Our x values are in negative land, right? So we actually here have to take the negative square root. If this had intersected in either quadrant 1 or 4, we would take the positive. But because we're intersecting in quadrant 2, we need the negative x. So this is, again, not the way that I would recommend doing it, but we're doing it so that you can comprehend the method and to verify also. All right, so here we go. The area should be the sum of the infinite slices from y equals low, which is what? Now, I'm not going to mess up this time. The smaller of the two y values is what I'm calling b to 2. So the integral from b to 2 of the curve on the right, which is the natural log of y minus 1. Or you can call it x sub 1 if you want, minus the curve on the left, which makes it plus the square root of 2 minus y. Now, in this case, I don't think there's a real advantage to calling it x sub 1 and x sub 2 other than the setup, because you still have to type those equations in. It's not like you can recall them from y1 and y2. But when you subtract the negative, notice it turns to positive. So there would be your integral setup. Back to the home screen now, math number 9, from alpha b up to 2. And even though they're y's on our paper, we still type them in as x's on our calculator. So we got the natural log of x minus 1 plus the square root of 2 minus x with respect to x. And with any luck, we should get the exact same answer. Do we? It's only correct to the first 6 decimal places. After that, they differ. But it is the same answer, right? The calculator is limited, I guess, in its programming abilities to make them both exactly act the same because of the way it's doing it. We're required to report 3 decimals. And to 3 decimals, your calculator, regardless of the way that you do it, should be accurate. Of course, there's a little bit of interpretation sometimes. 0.999 something is usually a 1, and 0.0000 something is usually a 0. Which one of those do you think is actually more accurate? The top one or the bottom one? It should be a function of how long it took the calculator to work. I don't know if you remember which one took longer. The first one's more accurate? Yeah, I think the first one's a little more accurate. Anyway, they both work. That's great. Now, if you are heck bent on using y from the home screen instead of x because it's y on your paper, when you're setting up your definite integral, you can actually use y. You can say it's alpha 1. Oh, now I got the spinning beach ball. Y minus 1, 2 minus y. And you only have this option on the home screen. If you're doing it from the graphing screen, you have to call everything x, not L1. Stupid mouse and delay. Come on, come on. Alpha 1. Come in, alpha 1. Now, here's why you can define it to be y. This dx right here, that's where you define the variable. And as soon as you define the variable there, it treats this and takes away whatever might have been stored as x or y and now treats it as a variable again. And you get the same thing. So you could use alpha m there if you want. But why do we still use just plain old x? Because there's a shortcut key for x right here. You don't have to hit alpha x. You just hit x. And It saves keystrokes, which saves time, and time saves money, right? So you become very rich over time. Yeah. Okay. Very successful, very rich. Not a loser, right? Many successful companies all over the place. Yeah. I don't know. I got out when the getting was good. You're going to have to ask Christy about that. Hey, anyone ever been to Johnston Island in Kiribati? If you went skydiving there, this is probably what you saw. No. Okay. Any questions on that? Once again, we only pick up the calculator when we need it, right? Not from the very beginning. We think through the problem first, and we set up our integrals, we set up our derivatives, we set up our equations that we're trying to solve, and then we pick up the calculator. All right, so we're done with the section. The last little thing here is just a segue into what we're going to be doing. We're going to be finding volumes in the next section with a two-dimensional integral. Remember, the integral is two-dimensional because when we first were exposed to it, we were finding areas of regions, right? And we used Riemann sums. So when we did Riemann sums, let's review that. You had an x-axis, a y-axis, and we had little rectangles here. And this was our function value, and this was our width, which we called dx. And we just integrated from a to b. F of x here times dx. This f of x represented a height, which is a one-dimensional quantity. Dx represented a width. Height times width is going to give you area. But here's what's cool about the integral. The integral itself is just a very systematic way to add up a bunch of things from left to right, assuming that you can write a function for them. The dx is always going to be dx. It's going to be one dimension. But if I could somehow write an equation for, instead of the height, which is one dimension, in the next section, if I can come up with an area formula, and I can then multiply by dx, this is going to be like length times width times my third, well, let's call it length times height. Length times height times the width. Guess what that's going to give us? Length times width times height gives us volume. Now, the key is, are you able to write the equation as a function of a single variable for the thing that you're going to be integrating? AB is also going to do this, or BC, sorry. Y'all are also going to do this. You're going to write an equation for the square root of length times dx. Now, what does the square root of length give you? Yeah, this is going to give you distance. You're going to have a one dimension. You're going to set up the integral to give you a one-dimensional thing. So we can use the integral, which starts off as a two-dimensional integral. We can use it to find a three-dimensional thing. We can use it to find a one-dimensional thing. It's all about whether or not you can come up with a single equation that represents that function. Okay, and that's all this is saying right here. All right, any questions on area? Yes, I did. Yes, I did. 5 and 6 were different answers. Let's come back. If I re-recorded it in fourth period, so 10/3 is the answer. What happened here is I didn't distribute this negative. I did it all in my head. 4 minus 2 is positive 2. What should I have done? Distribute that. So this positive 2 right here should have been a minus 2, and that was really the only difference. I should have subtracted 2 instead of adding 2, and then it came out to be 10/3. And that's all it takes. One little negative there can ruin your whole day. So anyway, be very, very careful. Even with parentheses and brackets, you could be diligent. But, you know, the more you try to do in your head, especially quickly, sometimes you can make real careless mistakes like that. And it's good to call them careless instead of stupid mistakes. Don't call them stupid mistakes, because that could take a toll on your psyche, right? Just call them careless mistakes. Yeah, you'd rather be careless than stupid, because you could learn to be careful. You can force yourself to be careful. It's hard to fix stupid. Yeah. Okay. That's it. Any questions on the worksheet? Y'all started it. I know that y'all are almost done with y'all's third draft.